For this problem, suppose that an eavesdropper, Eve, knows Alice is sending Bob a message, M, which is in the set 00, 01, 10, and 11, using a one-time pad where the key K is a perfectly random key unknown to Eve, and the distribution of messages is uniform, i.e. each message is equally likely. What is the conditional probability that M equals 01 given that Eve intercepts the ciphertext 01? Give your answer to 2 decimal places. For this question, we have the same information that we had in the first problem, and additionally, suppose Eve learns that Alice generated the key K using a biased random number generator that outputs 0 with a 52% probability. What is the conditional probability now that M equals 01 given that Eve intercepts the ciphertext 01? Submit your answer with 4 decimal places. This question asks about perfect ciphers. You should assume that M1 and M2 are messages selected from M, the set of all possible messages. You should not assume that all messages are equally likely. C is a ciphertext selected randomly from the set of all possible ciphertexts. K1 and K2 are keys selected randomly from K, the set of keys. And the question asks to check all statements that are true. If a cipher has fewer keys than possible messages, it is not a perfect cipher. AES is a perfect cipher. If the probability of M1 encrypted using the key K1 equals C is greater than the probability of M2 encrypted using the key K1 equals C, then E, the encryption function, must not be a perfect cipher. In the last statement, if E is a perfect cipher, then the probability of M1 encrypted using K1 equaling C is equal to the probability of M1 encrypted using key K2 is equal to C. This next question is about an application of symmetric ciphers. To exploit the beast vulnerability in HTTPS, suppose an attacker has intercepted the ciphertext, which, using 4-bit blocks, C0, the first block of the intercepted ciphertext, is 1000, and is the result of encrypting M0, the first block in the message. C1 is the result of encrypting the second block in the message, and C2, the result of encrypting the third block in the message. Our attacker wants to find if M1, the second block in the intercepted message, is equal to 1010. And the question is, what should the attacker use as a target value for M0 prime, which is the first block in the next response? And your answer should be 4 bits long. This question is about key distribution. Suppose Alice and Bob execute the Diffie-Hellman protocol, but pick a value for G that is not a primitive root of Q. Which of the following could happen? Alice and Bob could produce different keys. The generated key would be more vulnerable to an eavesdropper. The number of possible keys that could be generated would be smaller than Q. Or an in-the-middle attacker would be more powerful than if G is a primitive root. Check all that apply. For this problem, let M be a 2-digit number. The value of M is encrypted using RSA and Alice's private key K, using no padding, like this. Given the values of Alice's public key and C, the ciphertext, in the instructor's comments below, what is M? We would like to add digital signatures to the course accomplishment certificates that would allow someone who knows KU of CA, the public key of a certificate authority, to validate that a certificate was generated by Udacity and earned by the person whose name is in their certificate. Assume M is the certificate string, for example, Certificate of Accomplishment with Highest Distinction earned by Alice Hacker in CS387. Assume E is a strong public key encryption algorithm, H is a cryptographic hash function, and R is a random nonce. Which of these schemes will allow Udacity to generate unforgeable, verifiable signed certificates? Check all that are valid. For this problem, we ask about the missing step in garbled circuits as covered in Unit 7. At the end of the garbled circuit protocol, the evaluator has the output wire labels X1 through Xn. The generator knows the corresponding semantic values. For notation, X10 is the wire label corresponding to a semantic value of 0 for the wire 1, and X11 is the wire label corresponding to a semantic value of 1 for wire 1. Suppose the generator wants to reveal the result to the evaluator without revealing any other wire labels. Which of these 5 options would allow the evaluator to correctly determine the semantic value of the wire label X1 and not reveal the other output wire label? Check all that apply. The Bitcoin protocol relied on using proofs of work to provide scarcity in producing new blocks. For this question, you are asked to order a list of tasks by how much expected work they require. Assume that H is a strong cryptographic hash function that produces 128 output bits from any length input. Computing H of X takes 1 unit of time. E indicates RSA encryption. K sub U is a known public key, but the corresponding private key is not known. Computing the encryption of X takes 1,000 units of time. There are no memory limits. but the task has no access to pre-computed values. Using those assumptions, order these by how much work they prove, from the least expected work to the most expected work. For example, enter CEBAD if you think C requires the least amount of work and D the most amount of expected work.